we can get all of these different keywords from the topic, and in this case, calculus. And we also talked about how it can be overwhelming, but it's important that we just go through and ask these questions, especially the why is it important, because that's what is going to give us relevance. This is the thing that gives us the problem to solve, which is the thing that, remember, the order of learning is important. We need to have that application of learning coming as early as possible before we even try to understand the theory. We want it to be purposeful. We want to learn in order to solve the problem. We don't want to learn and then solve a problem. The order is very important. What is the problem first, and then we learn to solve it, not what is the information and now try to solve some problems with it. It's the wrong order, and it's a very important cognitive difference that we need to be very, very clear about. So now let's shoot on this. Once we shoot on this, what we see is, and the other thing is, we are aiming and shooting every 3 to 5 minutes, like I've demonstrated in that aim shoot cycle. We're constantly going back and forth. So for me, I was going back to the aim every 3 to 5 minutes, referring back to this list so that I could keep looking at, okay, I just learned about this. Oh, how does it relate to any of this stuff? Oh, is that different or the same to any of this stuff? I'm constantly going back and asking those types of questions. So let's see how the shoot step looks like. What I simply went and did is I got the information, all of that information, and I simply asked those questions. And when I answered those questions, I mapped it out in my head, and I tried to see how the relationships can be represented on the page in as simple as possible. So here I've got a basic structure, you can see. So this is the structure of our knowledge. We have the idea of functions and inverse functions. And when we're calculating the rate of change of these, that's effectively what differentiation does, which produces us a derivative using chain rules. And the way that we apply this is through some of these different examples. And then that derivative can be calculated further through operations. An example of differentiation and derivatives being used is finding tangents and normals. Taking a derivative and doing the opposite, differentiating, going back to the function, is actually called anti-differentiation, which gives us the functions. Whereas on the other side, we've got integration, which is very similar to anti-differentiation in that it produces what's called an indefinite integral, which is contrasting to something called a definite integral, through which we can use to find area, whereas other types of integration can be used to find the rate, average values, or different types of areas. So I've split this up into different processes and different functions. I had the basic logical framework being set up here, and as I learned more and more, I just added more and more detail onto it. So getting to this point took a decent amount of time. However, and when I say a decent amount of time, remember I was basically learning the subject from scratch again because I honestly forgot pretty much everything. So I literally all I remembered was that integration and differentiation are almost like opposites of each other, and that a derivative comes from differentiation. That's almost all I knew. And I knew what a function was. I didn't even remember what an inverse function meant. Okay, so I really looked up all of this stuff. So for me, I literally actually did this while I was in my car, sitting outside of a cafe while I was waiting for a friend. That friend happened to be very late. So actually, this took me about an hour and a half to do this. But by the end of this, I felt like I had a really strong understanding of not all the equations. At this point, I didn't know all the equations. I didn't know all the different formulae, but I knew exactly, once I learned that equation, I know exactly how I can use it. I had so many ideas about how I could apply that knowledge. I had so many examples of finding minimum and maximum and calculating the smoothness of a function, or figuring out stationary points, or looking at signed areas and how that could be applied in different types of scenarios. So what I had at this point is, without even knowing the equations, I was able to prepare myself for the most difficult questions, which is the applied mathematics questions. In my mind, I was thinking, man, there are so many different ways that you could apply this. I don't know exactly what I'm applying yet because I don't know the equations or how to do the calculations. But I know once I learn that, I know exactly what the purpose is going to be. So that purpose is locked and loaded and ready to go. And all I need to do now is go and learn how to do that. And it should straight away lock through and helping me understand that. So when I see students who struggle with the applied maths side of things, I know for a certainty that the way that they're approaching their learning is far too memorization heavy, and they haven't fundamentally aligned what they're learning with why they are actually learning it. So now, once I have this level of understanding, once I've got this level of understanding, I'm now ready to learn the equations, do some calculations, do some practice, and actually start getting better. And because I took the time to do this, I'm now going to save myself masses of time later because I've just flipped the switch. By doing that, I flipped this ratio. I've gone from a 1-to-1 ratio and I flipped it to a 10-to-1 ratio, where every question that I do is going to allow me to understand 10 more different types of question types. And I'm never going to be thrown off balance because I know exactly all the ways they could test me, because that's all the ways that I know this can be applied conceptually. So by spending a little bit more time here and fleshing out this part, it's allowed me to make this procedural aspect, learning to apply the maths, much faster and more intuitive and more purposeful. And we're going to see how we can take that to the next level using the skin step. But this is just a basic mind map that you can make. And 1.5 hours to get this level of logical understanding where you feel comfortable and actually confident with the topic despite not knowing any equations, doing that is very well worth the amount of time that you would spend.